In this video, we're going to be talking about priority queues. Now this is something that you're already very familiar with. So what we're going to be doing in this video is talking about the C++ library implementation of the priority queue and how to use it, but also talk about how it's implemented. It's implemented in sort of like the best way, I guess you could say. And so it's good to kind of see this new data structure and how it's implemented, which we'll mostly cover in the next video. So a priority queue is an abstraction where you can keep the items that are inserted into the queue in order by their priority instead of just in order by how they entered the queue or how they were in-queued. So we do this by just having key value pairs, where in this case the key is the priority. So 1, 2, and 3 are inserted with the data itself, 1, 23, 98, and 4. And that is the way that it's kept track of which item goes first. And then, of course, with ties, you have to also consider what happens. So it's a really great example of an abstraction versus a data structure, because a priority queue is one of the abstractions that can be implemented so many different ways. It can be implemented with a tree, as you know, and it's a really natural implementation, but it has actually, especially a binary search tree, has some features that make it kind of unnatural for the priority queue. You could also implement a priority queue with just a list or a vector, or pretty much anything else you could think of, as well as linking up lists in different ways. So there's really a lot of options. So I want to talk today about sort of the most ideal one that's used most often. So before we do that, we're going to actually talk about how to use the C++ library priority queue. So it comes with the queue library, and I want to emphasize that the priority queue implemented in C++ was implemented in a way that it could be incredibly general. So they made it so that you can order the priorities by ascending or descending order, but also like the sky's the limit, and that's controlled by a function object that you provide, which at this point we've kind of seen quite a few times, and maybe is starting to make a little bit more sense to you how that might work. So you call the priority queue to construct one, but then you have to provide all these types in the declaration call. So it's in the queue library, but the type is priority queue. And then you'll see there's 3 lines that we have to use in order to just get the type of priority queue that we want. So first we have to indicate the type of the key and the value pair. As a note, the second item in the pair is actually our key for the way that we're setting up this priority queue. And you do have to use the pair type in the priority queue. So we're having both integer key and values. So that's the first thing. The second thing is very confusing right now, but it will make sense actually after the next video. You also have to indicate which container you're going to use to set up the priority queue. So priority queues use trees, but they store them in a different container. And so the default is a vector. So if you didn't indicate this, then it would use this by default. But we have to call it because we need the third call here. And so we need to put something in the second call. So the vector is what we're going to be using, and basically, to give you just like a little bit of a spoiler of what we're going to talk about with how it's implemented, is that we're going to implement a tree using a vector. And so you need to tell it which kind of container you want to do for that. The third is the function object. So we're calling the function object prioritize, you can call it whatever you want, and it's going to be defined on the next slide. But this is that function object that determines what order the priorities are actually going to sort the priority queue in. So are you going to put the smaller priorities first or the larger priorities first, basically? Obviously you can do a lot more, but that's usually what you want to do. So PQ is our variable that we're using for our priority queue, and then to insert into it you use push, but you do have to set up pairs. You might actually want to use the priority queue in some of your projects remaining, and so this is just a nice template code that you can use to kind of see how all of this funky stuff works. So the first way is you can call pair, and you can use this syntax here, but you can also use the syntax make pair, so they both do the same thing. So that's going to set up this priority queue here, and you can see that regardless of the order that we insert these different pairs into, it's going to keep them in order of smallest to biggest. So I'm going to talk about now the prioritize function to see how you can indicate that you want it sorted in this order. So prioritize is a function object, a functor, that's set up this way. You set up a whole class and you call it whatever this functor is called, and then you set up the operator for comparison, and you pass in the same types here that you use as the key value pair. You always set these up as constant, and it actually forces you to do that because you don't want this comparison to change your underlying data, because that would be never intended. But we do pass by reference to save on memory and not making copies. So we're just passing in two key value pairs. I don't know what that was supposed to say. Key value pair 1 and key value pair 2. So if you want it to look like this, where you have at the top the lowest priority, or at the front the lowest priority, then you're going to set up your return as this. But basically, if you want smaller values at the end, return true if P1's value is less than P2's value. If you want larger values at the end, which is what we have here, return true if P1's value is greater than P2's value. And then here you'll notice that we're calling on the second item in the pair because, as I told you, the second item is the key in our example. Right here. So that's how you basically can use the built-in priority queue. Again, it's really not nice syntax, really, right? It's written in a way to make it general, not in a way to make it clean syntax, and that's generally how C++ is. Okay, so let's just talk about a couple things about the priority queue. So first, again, I've emphasized this 1,000 times, but these priorities are not limited to integers. They can be anything you want. So here's some priorities that are doubles, but they could be anything, any other type you'd like. You just have to indicate how to prioritize them. The priority queue is implemented on a heap data structure, which is a tree implemented in an array, which we will talk about. And the priority queue using this type of data structure does have fast pop. So it's able to grab that first element in the priority queue efficiently. It's still log n time. It's really efficient to look at the top, so to not pop, but to just do top, which is what it's usually called in most abstractions. That's actually 01, but it's not fast search, and you'll see why in a minute. So it's not a data structure that you use if you need to search. It's a data structure you use if you just need that first item in the list. So it's implemented using a min heap. It could also be a max heap. So it's implemented using a heap. And we're going to talk in the next video all about what a heap is. But let's first just look at the heap in tree form. I just want to make sure I don't forget anything that I wanted. Oh, here we go. So a couple of things. First, you'll notice that a min heap is a binary tree. So every node has at most 2 children. But what you'll also notice is that the minimum value of this tree is at the root. And so you have access to the minimum element in O1 time because it's the root. So if you ever want to know what the minimum or what the first item in the priority is, that's always O1. If you need to remove that, as you can imagine, once you remove one from this tree, you're going to have to restructure the tree, and that does take the height of the tree to kind of move everything to the right spot, but access to it itself is O1. So you know that you can see here that the minimum value is at the root. So what other things do you notice about the tree? You might notice that the parent value is always less than the child value. So not only is the root the smallest, but if you go to any node, the parent is less than the two children. You'll also notice that it's not a search tree because there's no relationship between the siblings. So if you wanted to look for something in this tree, you wouldn't really know where to go. So for example, you have 1, and so if you're looking for any other item in the tree like 15, how would you know whether to go left or right? You wouldn't. You would actually just need to traverse the tree to be sure. So it's not a data structure you would use if you need to search your tree. And this would be called weak ordering. So the data structure has weak ordering because it doesn't really have strong ordering, right? It has some order, we know top-down order, but we don't understand fully the order of the items in the data structure. The other thing you might notice is that this tree is balanced, and it's not obvious when you just look at one example of a tree, but a min heap maintains ideal balance because as you insert in it, it keeps the tree completely full. So it doesn't add leaf nodes until the whole level is filled. And so it always stays balanced, which makes that log n complexity of removing an item from it really safe. So we will talk in the next video all about the min heap and how you can implement it with an array, and that allows for some really nice efficiencies in space efficiencies. And for now, I just wanted to do a quick aside because we've started to talk about a lot of different abstractions that allow you to keep things sorted. So we know that maps are really, really useful for keeping stuff sorted because as you put stuff into the map, the underlying data structure of the map container in C++ keeps it sorted. So when you need to keep your data sorted, a map is a great thing to use. But now you also know that the priority queue is also able to do that by keeping it in sorted order as well. It has it's a totally different abstraction that allows for different things, but it also keeps your data sorted. And then you also know that you can just sort your data using the sort algorithm. So with sorting your data, you call the sort function, which we've done. And one thing that we didn't do is talk about how many different ways you could sort. And so here is an example of using a function object, which you may or may not have used in the past in order to sort data using the built-in sort function. So they're really useful. You can use them all over the different containers and abstractions in C++. But I really wanted to talk about this just so you could kind of step back and think about sorting, because a lot of times when we're solving problems in software engineering or computer science, it oftentimes requires you to think about sorted data and how to keep it sorted or if it needs to be sorted. And so as you're kind of adding all of these tools to your tool belt, it's good to kind of conceptually map them into your head of what the tools do, right? So maps, priority queues, or vectors that are calling some sort algorithm can all, keep things sorted, and they're all very different in the way that they do that, and different there's different uses for each of them. So that's all we are going to talk about here with priority queues. Stay tuned for the next video where we're actually going to go into heaps, and that will help understand the priority queue much better.